My name is Jay, and this is on the energy efficiency of unoptimized code. So first we have to talk about what we mean when we say energy efficiency. Coding languages are not just different because of their syntax. They're also built differently, which means that there's a resource cost difference between these languages. Also, the way a program is run also affects the energy requirements of that program. For example, a program that's compiled talks directly to your computer's operating system, whereas a program that's interpreted has to go through a translator first, which requires more energy. Many different factors go into defining how energy efficient a language is. We're going to be talking about these four: LLC misses, which is how fast the cache memory fills up, basically how much memory is required. Cores required, that's how it handles complex programs. Does it break it down across many different cores, or does it keep it in one? Power draw, how much energy it consumes. And runtime, how fast it runs a program. Now, runtime is not really energy efficiency, but it does influence how we as programmers choose our coding languages. So some previous research on this. In 2024, Van Kempen et al. Published on the energy efficiency of programming languages. This investigated the energy efficiency of around 14 different languages using a pre-made suite of optimized code. We can see their plot on the right here. There's little difference in the average power draw between the language implementations, which kind of supports their conclusion that the choice of programming language has no significant impact on energy consumption beyond execution time. This is the study we're trying to emulate. We based our study off of this one. We're using a lot of their code. We are trying to replicate their results, but there are some differences between our study and their study. So students working with languages they don't know or techniques they're unfamiliar with, as they would when they're starting on Atlas, naturally would not write the most efficient or optimized code, nor would we expect them to. So we need to understand how that influences the results from Van Kempen et al. We're using student-created, unoptimized code as our benchmarks rather than the optimized suite that they use. These benchmarks also use root, which they did not in Van Kempen et al. And instead of using 14 different languages, we're using 3. Python, compiled C++, and interpreted C++. On the left here, there are some plots from Van Kempen et al. That we're trying to emulate, but you'll notice that our plots later look a little bit different from theirs, and we'll talk about that. So why do we need to investigate this? In 2015, the United Nations committed to 17 Sustainable Development Goals to be met by 2030. This includes Goal 13, which is to take urgent action to combat climate change and its impacts. Energy consumption does influence climate change. The more energy consumed, the more it impacts climate change. So it's our responsibility as researchers to limit our energy consumption in order to assist with this goal. Atlas has begun pushing for new members to use Python rather than C++ due to the language's simplicity, but since Python is an interpreted language built on C++, it'll always be less energy efficient. So we need to ensure that the energy efficiency difference between Python and C++ is not significant enough that it works against the efforts of Goal 13. So here are the benchmarks we're running. All of them open a root file and then plot a root histogram, but how they do and what they're doing is a bit different. I'm not going to go over all of these, but what you do need to know is that root 1 and root 2 do the same thing, but they do it in a different way. 1 uses a for loop, and then 2 uses an R data frame. Delta R plots the delta R between T Lorentz vectors plotted for each event that has 2 electrons. And complicated is, by its name, complicated. It's just meant to emulate something that requires a lot of energy, that needs more resources to run. And we'll see if it does that in a second. So the data. Here are the LLC misses plots. So some observations we can make is that despite the fact that 1 and 2 do the same thing, there's clear differences in their LLC misses plots. For using for loops creates differing memory usage. We can see distinct grouping based on language. And our data frames create select memory usage, where we can see they're all kind of in the same region. This makes sense if you know that our data frames is built in C++. So when Python runs it, which is also built in C++, it'll just run the C++ code instead of like translating it into Python or whatever. So all of these languages are running the same subset of code when using our data frames, whereas for loops are different in every language, and so they run differently in every language. So this makes sense. We also notice that generally Python requires the most memory and compiled C++ requires the least memory. This is also expected. You might notice some oddities about these graphs, which we will talk about later. So here are the active cores plots. So some observations we can make. The most clear thing we can see is that the average number of active cores is generally the same across all the languages and tests. It's around 1. Now, Python occasionally has greater than 1 active cores, but only by a small amount. So this all lends to Van Kempen et al.'s hypothesis that there's no differentiation between, or there's little differentiation between languages when running, in terms of energy efficiency. So we can see that. This is very interesting. So the runtime and energy consumption by language. Some things we can notice is, first thing we can notice is C++ always has the least energy consumption and runtime, often by a significant amount, even with the complicated programs. We would expect this since the other languages are built on C++, but it is interesting to notice how large the difference is in certain cases. We can also notice that our data frame seems to require more energy consumption than a for loop in all languages, and then it's not consistent whether C or Python have less energy consumption or runtime because they switch back and forth between having the most and having the least. Which is interesting. It's an oddity. It's not something we would expect to see. And so that kind of requires more investigation. Our last plot of the day, this is that plot that we showed at the beginning, or our version of it. So what are the observations we can make about this plot? The main observation we can make is that it's a really terrible plot. We can't draw the conclusions that Van Kempen and al. should, and I'm not sure that they should have used that plot to do it either, because this plot is leaving out very important information. So we can see that C++ has the highest average power draw, or the point with the highest average power draw out of all the languages, which is odd since it seems to have placed last in every other plot so far. Very interesting. We can also notice that Python and interpreted C++ have the lowest points, which is also odd, and that they all have generally the same ranges, which does support Van Kempen et al.'s hypothesis. But the problem with this plot is point density. We can't tell where the density of these points are. It's possible that compiled C++ is near 5 and Python is near 6, but we can't tell. So we need this to do is have this be a histogram. But that wasn't included in Van Kempen et al.'s plotting. So this is something we'll have to look forward to doing in the future. So conclusions supported by results. I'm not going to go through these because we've actually touched on all of these so far, but you can read them if you want. The main thing you need to know is that all of our results do in some way support the conclusions made by Van Kempen et al., but they're not as direct as you would have liked. And they're supported by the results, but we can't actually draw any conclusions from the data we have so far because this project needs more benchmarks and testing and to fix all the oddities before any formal conclusions can be made. So here are some limitations of the project that need to be addressed. Number of benchmarks. There are only 4 benchmarks with similar code being run for all of them. Like they're all using root. And even still, the results don't completely agree, which is a bad sign. There's 1 singular author. All the benchmark code is written by me. So this project can't be extrapolated to all students on Atlas, working on Atlas, because it's just my code. The plots are ineffective. We discussed that earlier, but you can see another example in the bottom right here. Hardware, the computer being used to run these tests only has 3 CPUs available for computation, whereas Van Kempen et al., I think they had 120, which is a huge difference and may limit the results. I don't know by how much, but it's possible that it would. So what is the future of this project? Standard process for running benchmarks has been created, so more tests can be run very easily. We want to get more students to write the same and new benchmarks and then rerun the task. So if you want to participate in this, you can contact Heather Russell at this email address. There are also some oddities that need further investigating. We mentioned some of these earlier, but why are there 2 distinct groups of C data here? Why does interpreted C++ behave so differently here? Why does Python behave so differently here? And why does our data frames require more energy consumption than a for loop? We don't know the answers, and this requires more investigation. But that's the end of my time, and it's the end of my talk and my time on the project. So, yeah, if you have any questions, let me know.